Hi, I will present the texture mapping and defect detection. The goal of this step is to have a bridge geometry and unsorted images as an input and generate a high resolution surface texture of the bridge and defect information as an output. We have collected data for the input, so basically high resolution images from 10 bridges around Cambridge, which were the same bridges as you have already seen it in the as-is modeling. So 10 bridges around Cambridge, concrete bridges, simple geometry, no train bridges, no water crossings. So these are the 10 bridges. And we used an equipment for collecting the data, which is quite sophisticated. So it's a high resolution DSLR camera. It has 42 megapixels, a zoom lens so that we can actually shoot images or record images over traffic lanes. And for the high-lying areas, we have a high pole, an 8-meter high pole, and or tripod, and a remote control tablet. So this way, with this equipment, we could record most of the bridge elements without any traffic control. We took about 3 terabyte of data, so it's a lot of data for the 10 bridges, and we try to cover all the surface parts, all the visible surface parts. So some of the findings: the bridges we've collected data from are in a fairly good condition, but we still found some defects. For example, you can see a nice little crack over here. That's a bearing wall. Or over here you can see a crack in this column. Here you can also see a crack and some marks of a former inspection. Here's also a crack. Some spalling. So here is probably from a truck hit. You can see here some spall. Again, a spall with reinforced, where you can see the reinforcement, exposed reinforcement, and here you can see some discoloration. So this green color is the discoloration, some bleeding, efflorescence. So there are quite a lot of defects we can find, which we have collected. So now the first question we have to talk about is how do we actually get the images onto our bridge. Yeah, there's something called photogrammetry. You've probably all heard of it. So basically what you do, if you have you take images of the same object from different perspectives or from different angles, and from what you see, from the features you can see on that object, you can identify the 3D shape of that object. But actually the photogrammetry does two things. It does not only estimate the shape of the 3D object, but it also estimates the shape of the position and orientation of the camera. So what we would expect after doing our photogrammetry reconstruction is something like this. So this is a point cloud from a laser scanner. But what we actually got after 3 weeks of calculation is something like this, and it's pretty hard to identify a bridge in there. So actually there's a lot of errors. It doesn't work well for many reasons which we found out, but it doesn't work well. What we found out is if we do it just on an element, so element wise, the reconstruction works quite well. Not for all elements, but for many of them. It doesn't work for all elements actually, for the reason that it's not very easy to collect the right data. So you have to control which angles you are collecting and so on. So once we had that, we were able to use our 3D point cloud, our element 3D point cloud, and the 3D geometry of our as-is modeling, basically put that into place and then follow a simple ray tracing algorithm to recover the surface texture. And this is something we got out. So this is a column texture you can see right here, a reconstructed column from a real bridge around Cambridge. And you can even see the grass over here on the right side. Yeah, and this is low resolution. So if you zoom in, you will find that you can identify aggregates and little cracks, and the resolution is really high. So once we have that texture reconstructed, we can actually put that onto our as-is model and look or visualize it in 3D. So here you can see a column with the texture on top of it. And with that 3D geometry, that textured 3D geometry, you can actually have some fun. So we did two things. One thing was using a Vive and a virtualizer to bring that bridge model, virtual bridge model, into virtual reality. And actually, with a virtualizer, you are able to walk around in that virtual model. So you are in a virtual space, you can move, you can change direction, you can kind of remotely do an inspection on the real bridge. So remember, this is the as-is geometry and the as-is bridge texture you can see right here. So the same as it would be if you go out to that bridge and inspect it on site. Or you can use a HoloLens and just look at it in your office. So you don't even need that virtualizer and the virtual HTC Vive. You can just open up that model in your office space and inspect it there. So the next thing then, once you have that texture on top of the geometry, is to do the defect detection. The goal of that defect detection is that we have an input, which is basically an image, so the 2D texture, and we identify any area of interest or region of interest. So we want to reduce the search space, just the areas which might be of interest. So in this example, there might be a crack, there might be a little spall, there might be some suspicious areas which is not really clear, but many or most of the texture is actually unsuspicious. So that's our first step in the classifier. We do that by having a sliding window, and we classify each window separately. The reason for doing it this way is that there have been impressive developments in image classification using deep neural networks recently, but they are still very limited regarding the input size. And we have, on the one hand, we have that really large images, and on the other hand, we have a restricted input size, so we somehow need to find a way to combine that properly. And for each image patch, we then do a decision if that image patch is suspicious or not. So we have, for training our classifier, we have labeled a data set. You need labeled data for training such a classifier. That is quite complicated, but here you can see some results. So on the left, you see the texture, and on the right you see the classified results. So you can see that some of the areas, especially the areas which overlap with the background, that they are classified as false, but most of the area is actually classified as unsuspicious, even though you can see quite a lot of different textures on there. And then what we have done as an example, we added a spall, and we tried to make it as difficult as possible to seed. I mean, you can see the reinforcement, but color-wise and so on, it fits quite well. And as you can see, it was detected by our classifier. So then the next step, the detection step 2, is then to feed in each cluster of suspicious areas and make a classification for each connected patch. So basically we did the same thing, just this time we didn't have that sliding window, but we we trained for a complete defect. That is important because if you look at a spall, for example, If you split that up, each patch might look as unsuspicious, but in combination you can see that it is a spore. And because there's not enough data which we have collected from our own data set, we have got real-life inspection data from some DOTs, so Federal Highway Administration and Peterborough City Council and Georgia Department of Transportation gave us access to their inspection database and image database from the inspection. So this way then we can train a classifier to classify for each image or for each region of interest to give a classification. So rate if it's most likely to be a crack or a spall or no defect. And the results then is what we can present to an inspector, and he can decide how to continue. So from these two steps of the defect detection, the first step is almost done. So we are in the final evaluation phase. Defect detection 2 is still pending. So that is our next working package, which will be as part of my PhD, which I will continue even after this project. The training was done on high performance computer in Cambridge, which is quite fast. So we didn't use the full network. We only get a little piece of it or a little part of it. But actually, the important part is that the classification, then the result can be actually done on a mobile device. And the final part then was to embed all of this into a BIM model, so that you are actually able to store all of these results in a open format that is commonly used. And we used IFC. And here you can see the IFC viewer, or better, the software Gygax, which you will be able to play around with later yourself. So this is an IFC file you can see here with added textures, with added defect properties. So you can actually, we show and we published that you can embed all the information that is in a bridge inspection report. You can actually embed it into IFC without changing the IFC standard. So that already supports everything you need for embedding or integrating a full bridge inspection report. So to sum up, or the conclusion is that we are able to reconstruct high-resolution bridge surface texture. The methods are there. The problem is the data collection. So it's sensor-wise and especially location-wise, it is still quite laborious. And we can automatically extract regions of interest for inspectors with a precision right now of 86%. As I've said, that is work in progress, and we will publish results soon. And finally, that's done. Bridge inspection reports can be completely integrated into BIM. That is all done, and pending work is automatically classifying the defect type of regions of interest. So basically deciding if you have found a region of interest, what kind of defect it is. Thank you very much. That's it.